Okay, so first of all, let me say thank you to all the organizers for giving me the chance to present this work that we've been doing together on applying machine learning methods to try and accelerate the calculation of self-consistent Hubbard parameters. All of what I'm about to show is work that we've been doing over the last half a year or so with PhD students, Austin Zadeks, Kabinci, and of course, Yuri Timirov, all of us working with Nicola Marzari and Theos group at PFAD. Okay, so let me quickly just motivate what we were trying to do here. So as we've seen from Matteo, Yuri, and others, there is a self-consistent way to calculate Hubbard parameters, and perhaps the easiest place to start is to do a supercell approach, which of course comes with a certain expense. Yuri showed us how this can be significantly accelerated by using perturbation theory, but nonetheless, this is not what one might call a cheap method. And of course, we'd like to be able to get some of the advantages of Hubbard corrections, even in things like screening studies, where we maybe want to do a high throughput sweep over a number of materials. And that's simply going to be impossible if we're doing the full, even the perturbation theory approach, unless we already have figured out what the Hubbard parameters should be. But even then, it's going to be difficult for materials that we've maybe never considered before. So really, this is an attempt to apply modern machine learning methods to accelerate this procedure. Of course, there's a slight knock-on effect on the accuracy, but for the initial screening step of studies, this is probably acceptable, and then you can always dig into deeper details and do the proper calculations for the really candidate materials you want to look at. Okay, so let's gather together some of the notations and things that we'll need from what has been discussed this morning in order to build this model. And then we'll talk through some of the performance and transferability of how it actually works. So as you've seen, the Hubbard corrections are just adding this term to our DFT energy. And in a certain way, it's on the surface very simple, right? All we need is this U and V parameter. And then once we've got our occupation matrices, these ends, we can very simply calculate this energy. So for our machine learning model, we already start to think about, okay, what are the inputs that we want to feed into this thing? Well, for sure, the occupation matrices. If we already have a guess U and V, that can also go in as the input. And of course, the species of our either on-site, if it's U, or inter-site elements labeled I and J here. So as Yuri talked about, the occupation matrices are nothing else than projection of the Constant states onto some localized atomic orbitals, which will always have a spherical harmonic component, so they're eigenstates of the angular momentum. And these are always localized on the atom, so they have this property that they're invariant to translation, which will become important soon. Now, as Yuri showed, these can be calculated directly through using a perturbation theory approach. And if you do this, this is largely parameter free. There is, of course, the choice of which orbitals to project onto, but other than that, there's no parameters. But such a calculation can cost you on the order of 20 SCF calls, so it's not particularly cheap. And in addition to that, you also have the self-consistent loop that you want to do. So even if you know some initial guess that you've got from somewhere, you still want to check that this guess is reasonable, and you're going to have to go around this loop several times. And really the expensive part of this is step number 2, this DFT calculation. And you might need to do this 4 times or 5 times, might be typical. And so that's going to be 80 to 100 times 1 SCF call. Now, what we wanted to ask ourselves is, well, can we just skip a lot of this? Can we, in fact, just go straight from, let's say we have an initial guess for U and V, or it can be 0 if we really don't know anything. Ask a machine learning model to predict the final self-consistent U and V parameters, and then just do one final geometry optimization with those. That's the absolute goal, and hopefully I'll be able to convince you that we managed to make that reality. Okay, so for those of you that are interested in the machine learning aspect behind this, let me just quickly explain what I think are the pertinent features that make this model as performant as it is, and what's important in crafting any such machine learning model when dealing with the electronic structure. So of course, we want that our model respect the physical symmetries of the system that we're studying. So just as Matteo talked about, we want things that are invariant to rotation. So if we change R A and B, lattice parameters, we swap them, that's equivalent to rotation, but of course the energy, the Hubbard parameters and everything else that we're interested in stays the same. And it's not just rotations, of course, translation and permutation of the atom labels. So when thinking of the FT, this often is just built in naturally to the equations, but in machine learning models, this is not really the case. So I'll start with the graphs that I want to build my machine learning model on. So if I'm doing an on-site interaction, as I mentioned before, I'm going to put in the species label I, the occupation matrix, and if I have a guess, the guess U value. If I'm doing an intersite, it's basically the same thing, just doubled up. And the only new thing I have now is the distance between the two atoms. So the translation invariance we get for free because the atomic orbitals are always defined at the center of the atom if it's on-site, or the centers of the atom if it's intersite. The rotation is maybe the hardest part. So in order to get this, we're using a so-called equivariant neural network, which can take inputs that it understands the way in which these transform and the way the output of the neural network transforms with respect to rotations of the input. So just to give you an idea of how this works, effectively we take these occupation matrices, which, this can be if it's a P, it's going to be a 3x3. If it's a D, it's going to be a 5x5 matrix. And we decompose this into the irreducible representations. So in the case of the P, this is just this matrix decomposes into something that transforms as a scalar, that D equals 0, and an L equals 2 vector. Or if it's a P matrix, it's going to just have an additional component that transforms as a L equals 4 irreducible representation. And these inputs, the reason we do this is because this is a very natural way to encode this equivariance of the rotation. And we can use this package E3NN that we've been developing with colleagues, which can take these IRAPs or these IRAP representations as inputs. So if we do this, we automatically respect the rotational invariance or equivariance of our system. And then the final one is permutation of the atom labels. Well, the only one we really need to worry about is the spin up-down label. So of course, if the neural network was fed spin up-down and then you swap the two as inputs to the neural network, it wouldn't know that those were the same objects, just changed in label, and it wouldn't know that it should produce the same U or V value as output. So to fix this, we just create permutation invariant polynomials from the original occupation matrices. So the first one is nothing other than the sum of the two. So that's just a degree 1 polynomial. And the second input that we'll use will be just the Hadamard product. So the element-wise multiplication of the two spin up and spin down channel matrices. And for shorthand, I'll just call these 1 and 2. And these are the things that will then feed in, and you can see these quantities don't change if we just change the up and down spin labels. The actual models themselves, we have one model to predict a U value and an entirely separate neural network to predict the V. We have also tried doing it in one, but it turns out it's even more accurate to do it, to keep it separate. The general picture you can have in mind is this is a little bit more complicated because of the equivariance, but in essence, this is nothing other than taking in the things I mentioned, the U guess, the species, the occupation matrices, passing it through a bunch of nonlinearities, so these kind of layers you often see in neural network diagrams, and then spitting you out a scalar U value, which we then, of course, check against the training labels that we have from having done actual calculations through perturbation theory. And then we do gradient descent to fix up the weights and biases inside this neural network so it better represents training data. And the V value, the V model is just a little bit more complicated because now we have two sites to worry about, and of course the edge between them, which just encodes the distance, and the V carries the V value itself, the guess V value. Okay, so let's have a look at how well this performs in terms of both accuracy and data efficiency. So how little data can we feed it? The training set I'm using is a bunch of the olivines work from Uhrin. I also have some rare earth nickelates from the Kabinchi, and also some layered spinels from Uhrin. So we have a modest amount of data. It's not huge though. For the V values, what we'll do is we'll just take, for each of the elements that we have to play with, we'll take all of the data we have and split it 80-20. So 80% the model sees, 20% it never sees, and we just check how well it performs on those ones that it's never seen, because of course the labels it's seen, it should be able to give us a very good answer for. The ones it's never seen, is the ones that we're really interested in. So when we do this, here I'm just showing a parity plot, which effectively shows on the x-axis the actual value that's come out from a perturbation theory calculation, and on the y, the prediction made by the model. We see that overall across all of the species, the error made is about 151 millieV, and that varies a little bit between species. So nickel slightly worse, iron's reasonable, manganese is a lot better. But overall, this is really a very reasonable result for values that are of the order of 6 to 10 EV. To have an RMSE of 151 is already good. And keep in mind, this is a prediction for the final self-consistent U value. So you no longer have to go around this loop. You just do your calculation once, get the occupation matrices, feed it to the neural network, get the U value out, and then, of course, you still have to relax one more time. So that's effectively 2 relaxations that need to be done in all of this procedure. We can also just ask the model, train the model to predict the next step in the self-iteration loop that we have from our training data, just to see how well it really tracks the actual perturbation theory values. So the pink is always going to be the machine learning result. And we see that overall the trend is there. Tracking is not always perfect, but the scale here is something like 0.6 EV. So it's always pretty much within this range of 200-300 millieV error at the most. And of course, we need to check how the V values perform. Here we're lucky insofar as we have more data, because of course now it's a neighbor pair, so we have almost the square of the amount of data as we did for the U values. And the results are also encouraging. So the V's, of course, are generally lower values, between 0.4 and 1.2 EV, let's say. And the error on these is about 38 millieV on average, varying a little bit between elements, but roughly staying sort of in that under 50 millieV target. When looking at the tracking across the iterations, it's now very good. And in fact, the V's don't change that much between these self-consistent iteration steps. Now, there is a thing that we wanted to make sure, which is that, well, as I said to you, this model takes in the guess U and V values that you gave it. And so if those guesses are good, it's no wonder the neural network makes it a good output, because it probably doesn't have to change that value too much. So I filtered the data to look at just the 0th iteration, if you like. So the first time the perturbation theory was called. For the V values in particular, much of the training data I have has that V value set to 0. So there's no information about what the Hubbard V should be. And so the neural network's forced to learn only on the occupation matrices and the elements and the distance between the species pairs, but predominantly the occupation matrices. And in fact, the results are equally good, so 36 millieV in these cases. So it's really able to learn from what's going on in the electronic structure around these 2 atoms. Another very important point to go into is, of course, transferability. So as Uhrin mentioned, these U and V parameters are really very specific to the system that we're studying, and also the energy landscape that we're on. So, you know, what are the pseudopotentials that we're using, even things like what are the projectors. And so really it's fixed for those set of things. And we don't want to have to create new machine learning model labels for every different configuration within those parameters. So the landscape has to be fixed, but things like different oxidation states, perhaps even different crystal structures, we want to see if we can vary these, and the machine learning models still make reasonable predictions. So the first thing I did was to take the olivines data, so this LiFePO4 or manganese, and the numbers on the top are the amount of training points that I have for each element at different concentrations of lithium. So I wanted to see if I only train on just one of these, let's say half filled with lithium, and then make predictions to all of the other points, how good are those predictions? And then if I choose another, let's say fully lithiated, how good are the predictions? Or a combination of any 2 of them, or 3 or 4. So that's exactly what this graph is showing here. So what we're looking at is if I train on 1, 2, 3, or 4 of the occupation data that I have, how good is the error, or how bad is the error, if you like? And in fact, it's already reasonable after you train on 1. So even showing it just 1 oxidation state, if you want to think of it in those terms, the model is able to use what it's learned from that to make decent predictions for any of the other concentrations. But by the time you've shown it 2 out of these 5, it's already making very, very good predictions for the whole set. So this was for the iron. This is for the manganese. It's slightly worse. I found that the manganese seems to be a lot more difficult to learn in general, no matter what I ask of the model. But it's still, after 2, it's reasonable. By the time you've shown it 3, it can predict the other 2 oxidation states with a fairly low error. So this was all for the Hubbard Hubbard U, sorry. And if we now switch to the V, we play the same game. We see that already after showing it 2 out of the 5 of these, it's making fairly good predictions. So the transferability is there across stoichiometries. So we're changing the amount of lithium we have in there, which is changing the occupational matrices, and the model is still able to make decent predictions. The other thing we might want to do is, what if we don't want to go through this whole procedure of calculating the self-consistent loop? We just do the first step. We just calculate what is the first U or V value, in this case U, from the perturbation theory calculation, and then try to predict what would the result have been for the forthcoming steps, including the last one when it's completely converged. And again, the error is really very low, so 151 millieVs. Compared to, imagine you just called perturbation theory once and you said, okay, I'm not going to do any more. I'm just going to do a single shot, use that value of U. How far off would you be on average compared to the following steps, where you'd be making an error of around 400 millieV? So this model, even if you feed it data only about that first iteration, can already make a decent guess about where the U would have gone as you converge this thing. So let me just summarize what we've gone through and where the model's at and where we're going. So already the model can make very accurate predictions for the final converged Hubbard parameters with errors of less than 5%. Actually, many of them were 3 or even much less. On the data efficiency side, it's really very decent. So tens of HP calls are sufficient to give it enough training data to work on, so long as your system doesn't change too much. And that's seen in this transferability. So the stoichiometries, 2 examples are good enough. Self-consistent iterations, you can maybe even feed it just the first one. And different atomic environments is something that we're investigating now. So same element, but different crystal structure to see how well that performs. When can you get your hands on it? So this code that we call Hubbard ML will be released before the end of the year, including pre-trained models. So for the systems that we've shown here, there'll be a pre-trained model, and there's no need for you to calculate the HP parameters. Of course, if your system is different, then you will need to do some calculations that you feed to the neural network and train it. But all of that would be as automated as it can be, so it would be fairly easy to use. And of course, this will be integrated with AIDA workflows, so you'll be able to calculate Hubbard parameters automatically using AIDA workflows, and then pass this to the model, and then start using the machine learning part of it. The next steps after all of that is, of course, to automate this even further. So we're planning and implementing an active learning scheme where effectively when the machine learning model detects that it's making too large an error, it can at that point call the perturbation theory calculation to try and get a new training point, learn on that, and then carry on until it sees that it's making a too large error, at which point effectively everything would be automated. There's no need to manually train in the network. There's no need to worry if your result you're getting is accurate or not, because the neural network will automatically detect when the error is too large. And this last point, which is a little bit long-winded, but basically it sums up to, can we shave off even more DFT calculations? So at the moment, I was saying you need to do 2, effectively the first one, mainly there just to calculate your occupational matrices. And then the second one, of course, to relax the structure with the predicted U and V values. It's maybe possible that we can even skip that first one. We can just use the ionic structure, not even put in the occupational matrices to make a prediction of the U and V, to skip even that initial relaxation, which will leave just the one final DFT calculation to do. Okay, before I end, let me just thank SNSF, Marvel, and Dome, who fund my work, and for all of you for listening. Happy to take questions.
Thanks, Martin. Thank you very much for this nice talk. So I see there are a few questions on the Slack, so maybe I start reading some of those. So there's one question by JMO Lim. How large is the error in physical quantities like the relaxed structure or gap when using UMV from machine learning?
Very good question. So I haven't had a chance to do these. We wanted to calculate indeed exactly lattice parameters, also things like voltages. So I don't have an answer for you yet. My feeling is that this will translate into fairly low errors insofar as the machine learning model is making a prediction that's closer to the final converged U and V values than the first step of the first perturbation theory calculation. And that first perturbation theory calculation's U and V values are already pretty reasonable in terms of getting a good fix up to the lattice parameters and band gap. So my guess is that it's going to be better than that. But until I have the data, I wouldn't like to say for sure.
Great, thanks. Then there is another question. In slide 18, the data presented 1.8, the data presented a flat line trend. What can you say about that data, or possibly a reason for this? Not sure.
Maybe, so feel free to correct me. I guess you're referring on the right-hand figure, there's a bunch of purple dots that are kind of flat. So the right figure is showing if we just took the first perturbation theory call and take that value and now compare it with the subsequent steps that we know were done. But imagine we've only done one, but we actually know secretly what the answer is. So in this particular case, for this manganese example, also for some of the nickels, in fact, the initial value calculated by perturbation theory was quite wrong. And this is probably a bunch of self-consistent steps that are just moving away further and further from the first value that it calculated. So, I mean, to me, there's not much we can take away from this. This is just the answer that we get as we do the self-consistent loop. And that's coming from the perturbation theory, nothing to do with the machine learning. As you can see on the left, the machine learning actually makes a good guess for all of those down there in the bottom left corner, also for a lot of the nickels. So that's already encouraging.
Thanks. A question by Mukesh Singh. Don't you think that the training data are really small for machine learning?
Yeah, good question. Yes, I do. But this is the beauty of a lot of the progress that's been made in the last 10 years or so. So it turns out that incorporating a lot of things like, of course, locality, but a lot of the symmetry, so this equivariance that I mentioned, gains us a lot in terms of data efficiency. So if you're interested, a lot of the work is done on interaction potentials for the time being. So they're using as input the ionic structure. But the results are transferable. So for example, this paper by Simon Batzner and the group of Boris Kozinski at Harvard, so they showed that these equivariant neural networks, when used to fit energy landscapes for the ionic structure now, are orders of magnitude more efficient than even neural networks or other regression schemes we had just a few years ago. And so whilst I can't prove it, I think a lot of the reason why we're able to use so little data is precisely because we're incorporating all the symmetry information into it. And then in some sense, the results speak for themselves. I mean, whichever way we cut up the data, we seem that the model's still able to transfer reasonably well, even on a limited training set. So I think it's just really thanks to this progress in the machine learning side of things that we're seeing, examples where we can use so little data.
Thanks. Then a question by Matteo Cococcioni. Probably I missed this. What is the learning process based on? Crystal structure, also band structure? Does it contain also info on what pseudo potential you want to use? I guess you mentioned this, maybe good to eat.
Yeah, no, thanks, Matteo. It's important to make this very clear. So the choice of, let's say, the energy landscape, the the way that you're setting your system, the choice of pseudos, as well as the projectors, and of course, all of your other settings, the cutoffs and so on. That is a choice that the user has to make and has to stay fixed. So this model for sure cannot be used when someone's used one set of pseudopotentials and then somebody uses a different set and tries to use the same model. This really assumes that you've got just a fixed set of parameters for your electronic energy landscape, and then you feed in aspects of the electronic structure into the model. And the only aspects that go in are, if you have one, the guess U value that you've used, the species of the site or sites you're on, and the occupation matrices. That's it. We could potentially put in other information, but effectively it's just some local information of the electronic structure around the site that we're looking at, and that's it.
Great. Then I'll ask one question more. This is a question by Lorenzo Marti. Could you please provide some more details about the model architecture? Is it an ANN-based model, some kind of convolutional network, or autoencoder? Thank you in advance.
Sure, yeah, happily. So this is an equivariant neural network, which is very similar to a traditional feed-forward neural network that you would have for making any kind of prediction you like. The principal difference being that every layer, rather than being a purely linear layer, is actually doing an equivariant operation. So we do a tensor product instead of a linear layer, instead of just applying some weights and biases. And we do this always in the irrep basis, so the SO3 irrep basis. So when we take our inputs, do the tensor product, we get another tensor out that we then symmetrize so that it's also in a reducible basis of SO3 or O3 actually, because this includes reflections. And this gets passed through then a nonlinearity, which only applies to the scalar parts. And this continues. So you can have, you can repeat this unit if you like to have more and more layers in your neural network. I think in the U model, I use 2 hidden layers, and the V only 1. But conceptually, it's quite similar to a standard feed-forward neural network. In the details, it's a bit more complicated because we're respecting the rotational symmetries of the occupation matrices.
Great. So I see no other question on Slack. So I think we are perfectly on time. So really, thank you very much, Martin, for this talk.